Good day to everyone. I am Sam Wabina. I'm one of the lecturers for Mathematics and Computer Science track in Sync Tutors. And for today's discussion, we'll discuss calculus and numerical analysis, particularly numerical methods and optimization. Before our discussion, we're going to have a little overview about univariate optimization and numerical analysis, and we're going to discuss this interesting technique called bisection method, and we're going to calculate one example on how to use this particular method. In our early years of basic algebra, we have used different root-finding methods to find the value of x. For instance, if we have x squared plus 5x plus 6, we know the values of x are x is equal to 2 and x is equal to 3. And this is very easy to solve. There are lots of ways to find the values of x. We can use mental mathematics, quadratic formula, completing the squares, and even derivatives. However, in a world governed by complex systems and unpredictable variables, it is always challenging to find optimal solutions that are always present. From the mathematics that navigate our satellites to the algorithms deciding the stock market's next move, optimization is the silent engine driving progress. Yet, most real world functions cannot be optimized analytically. As we see in our slide, consider the function g of x log of x divided by the quantity 1 plus x. This function could represent a wide array of real-world scenarios, such as economic models or natural phenomena, and the goal is to maximize this function with respect to the variable x. When we find its derivative, or when we attempt to find the value of x by setting its derivative equal to 0, we confront an algebraic deadlock. First, let's find the g prime of x, which is the derivative of g of x. That is 1 plus 1 over x times log of x, and we equate it to 0 for solving x that leads to an algebraic impasse because it has no analytic solution. It is very intractable and it's difficult to find the value of x. So the derivative simplifies to this equation, which is a transcendental equation that does not yield to any traditional algebraic methods for finding a closed form solution. In many cases, the functions we seek to optimize are not just difficult to solve. They are nearly impossible to solve with just simple algebra. They require a different approach called iterative methods or iterative functions. They rely on successive approximation of the solution, and it might be a reasonable to use an initial value to find the value of optimal root. So in using or so they are so in many cases again the functions we seek to optimize are not just difficult to solve, but they are nearly impossible to solve with just simple algebra. And they require a different approach called iterative methods. They rely on successive approximation of the solution. And in using optimization, we usually assume an initial guess as our starting point. For instance, we consider t is equal to 0, where x of t is equal to x of 0 is equal to 3.0. That means 3.0 is our initial candidate for our root finding method. This value is not random, but a recent estimate that guides our algorithm's first step. The main idea of iterative method in optimization is the updating equation. It functions as a guide or as a navigator that, again, that guides our solution from our current estimate x of t to a new and improved estimate x t plus 1. Each iteration builds upon the previous honed by our updating rule. So in this case, the updating equation is based on the first order derivative of the g of x. That is g prime of x is equal to 1 plus 1 over x minus log of x divided by the quantity 1 plus x quantity squared. An updating equation will be used to produce an improved guess based on the initial guess from the most recent value of x of t for t is equal to 0, 1, 2, or until the iteration or stop or the convergent has been reached. The updated equation may be based on an attempt to find the root of this equation or on some other rationale. But in this case, most of the rationale or most of the updating equation is based on the first order derivative. So as we iterate, we inch closer to our goal, the maximum of g of x until we reach the best conversion, uh, or or the iteration will stop. So uh, as we iterate, we inch closer to our goal and the maximum of g of x. This process exemplifies the essence of numerical optimization, turning an intractable analytical problem, that is g of x, this is intractable problem, into a manageable computational routine. It is through these iterative steps that we harness the power of approximation to tackle problems that defy exact solution. So, for example, we have a graphical standpoint. Um, so here we have a graphical example. Uh, we have suppose we have a continuous function. This is a polynomial function. Let's say polynomial function denoted as f of x. This function could represent anything from a simple mathematical equation to a complex real-world scenario. And our objective is clear. We want to find the value of f of x is equal to 0. So f of x is equal to 0 means it lies here or along with the x-axis. In other words, we're looking for the roots of the function, which are the points where our curve intersects the x-axis. So in this polynomial equation or example, we have two roots actually. But let's just focus on the first root, particularly on the red circle. The red circle on this graph highlights one such root. And finding this root is not just a matter of solving an equation algebraically. It's about using numerical methods to approximate the solution, especially when an analytical solution is difficult or impossible to obtain. For our function here, we would start by selecting an initial sample. So let's say our initial value is here. Let's say our initial value is here. And then, since this is an iterative method that uses an updating equation per iteration, so per iteration, it improves the value of x or the approximation of x. So let's say for the iteration 1, it goes here. Iteration 2, it goes here. For iteration 3, it goes here. And until it reached convergence, this is the approximation. So it reached the optimal root for this function, for this polynomial function. So again, for our function here, for our polynomial function, we would start by selecting a numerical method based on the characteristics of f of x that deals with iterative method. It finds the optimal value or the solution through iterative steps. And this is the idea of numerical approximation or numerical analysis in the field of optimization. So this just answers the question, given a function f of x or a polynomial function, how can we find x? How can we find x that f of x is equal to 0, given that x is the root of this polynomial function? So this answers the question. This method or the iterative method, rather, answers this question. There's a lot of root finding methods in numerical optimization, and one of the most powerful method is the bisection method. The method or the bisection method uses the concept of intermediate value theorem or IVT, which states that a continuous function, let's say f of x, which changes signs over an interval a sub 0 or b sub 0, must have a root in that interval. It just means that if your function is a continuous function, which means it is differentiable, or it contains a derivative or differentiable equation, it means that if we have an interval a to b, between a to b, in that particular interval, there exists a particular root of that polynomial function or that continuous function. The bisection method takes advantage of this by iteratively halving or dividing the interval and selecting the subinterval where the sign change occurs, ensuring that the root is always contained within the interval. So let's focus on the condition outlined here, particularly on a much more theoretical standpoint. If g, if the function g is continuous, that means it is differentiable on the interval a sub 0 or b sub 0. This is the interval that I meant earlier, and the product of g prime a sub 0 and g prime b sub 0 is less than or equal to 0, so meaning it has two conditions before we use bisection method. Then the intermediate value theorem implies that there exists at least one x prime, or sorry, x star. This means the local optima that exists or that lies between the interval a sub 0, b sub 0, for which g prime x star is equal to 0. And hence, x star is a local optimum of g, or in other words, x star is a root of the is a root of the continuous function g. So this is the crux of the bisection method. We are looking for a point where the derivative of the function is 0, indicating a local optimum of g, which in the context of the bisection method is the root we are seeking. So to make it more understandable, suppose we have a polynomial function that is continuous and thus differentiable. The process is a model of simplicity. Bisection method works by starting with our initial interval. Again, initial interval, let's say a sub 1 and b sub 1. So we have a sub 1 here and b sub 1 here. These are our initial values. So, so if fa sub 1 and fb sub 1 have opposite signs, we compute f at the midpoint C. So C represents this big red point here in the middle of A sub 1 and B sub 1. Depending on the sign of f of C, let's say f of C, we select the new interval A sub 2 and B sub 2 to be either A sub 0 or C B sub 0. This method systematically reduces the interval size from A sub 0, B sub 0 to A sub 1, B sub 1, then to A sub 2, B sub 2, and so forth. Basically, if we have an initial interval A sub 1, B sub 1, A sub 1, B sub 1 rather, and then for the next iteration, we got A sub 2 and let's say B sub 2 here, and then A sub 3 and B sub 3 here. It means that the gap the gap between the optimal solution is getting closer to the correct answer with each iteration. So bisection method works by narrowing the gap between the positive and negative intervals until it closes in the correct answer. So this is the graphical explanation of bisection method. So let's go to their procedural framework. So I just need to have a recap. The bisection method is an approximation method to find the roots of the given equation by repeatedly dividing or halving the interval. This method will divide the interval until the resulting interval is found, which is extremely small. So in using bisection method, there are 5 steps. And given the 5 steps, they need to assume that they need to uh, follow the intermediate value theorem first. For the first step, let's say we have 2 points. They are normally given in the problem. Let's say A and B. These are the interval, or this is the interval that is given in the problem, such that A is less than B, and f of A times f of B, their product is less than 0. Recall that this is IBT, the intermediate value theorem. If we have the initial values A and B, let's find the midpoint of A and B. Let's say T. So basically, T is equal to A plus B all over 2. Okay. That T, that midpoint T, is the root of the given function if f of T is equal to 0. Else, we follow the next step, step 4, we will divide the interval AB. We'll divide the interval AB. If f of T times f of A is less than 0, it means that there exists a root between the midpoint T and A. Else, if f of T times f of B less than 0, there exists a root between C and B. Again, I just need to remind you that there exists a root between T and A if f of T times f of B is negative. And if f of T and f of A times their product is negative, there exists a root between T and A. And there's a root between T and B if f of T times f of B is negative. And we will repeat this 3 steps until f of T is equal to 0. Meaning, the convergence just says or just indicates that the iterations will stop if f of T is equal to 0. So suppose we have an example. Our first example is that we need to determine the root of the given equation, x squared minus 3 is equal to 0, for x lies between the interval 1 and 2. So A and B, or the initial interval, is 1 and 2, and our equation is x squared minus 3 is equal to 0. So first, we need to we need to uh, uh, have an assumption check first. Uh, we know that x squared minus 3 is equal to 0. This is continuous because it has a derivative. Its derivative is 2x, right? So it is a derivative, so it has derivative, so we can use the bisection method. And the given function is continuous, and the root lies in the initial value or initial interval 1 and 2. So let's say T as the midpoint let T be the midpoint of that interval. So we calculate T by 1 plus 2, that is the initial interval, all over 2 is equal to 1.5. Okay? So the value of the function at T is equal to 1.5 is negative 0.75. So we'll just calculate 1.5 squared minus 3. Okay, so again, to calculate this, we just 1.5 squared minus 3, that is negative 0.75, which is negative. Based on our theorem of bisection method, If f of t is negative, assume a is equal to t, and if f of t is positive, assume that b is equal to t. So since f of t for the first iteration, it is negative 0.75. So the value of a for the second iteration will be replaced with t is equal to 1.5 for the next iteration. And the value of b will still remain. So given that this is just an example for first iteration, let's have a closer look for the full iteration. Let's say we have a seven iterations. Given equation is still the same, x squared minus 3 is equal to 0, for x lies in lies between 1 to 2 in that interval. So this is the example that we performed from the previous slide. We have 1 and 2 as our interval, and we calculated its midpoint. 1 plus 2 divided by 2 is 1.5, and we calculated the f of t. Since f of t for the first iteration is negative, so a for the value of a for the second iteration will be changed to the value of t to the first iteration. Okay, and the value of b will still the same. It is equal to 2, but the value of a is 1.5, similar to the value of t from the previous iteration. So once we get the new interval, we will calculate again the value of midpoint, which is 1.5 plus 2 divided by 2, that is 1.75. And then calculate again for the value of f of t, which is 0.062. That is positive. Since f of t is positive, we will change the value of b for the third iteration, but the value of a will still the same. So we have since 0 it is positive, so a value of t from the second iteration will be the value of b, and value of a for the third iteration is still the same. And again, we will calculate the value of t, which is 1.625, and we will calculate again for the value of f of t for the third iteration, which is negative, and so on and so forth. So for this example, I just provided until seventh iteration. So at the seventh iteration, we get the final interval 1.7188 to 1.7344. By intermediate value theorem, uh, it consists a root which is 1.7266, and 1.7266 is the approximated solution only at the seventh iteration. But for the full calculation, for the full calculation, since the value of f of t should be equal, the value of t is equal to 0, it has not reached convergence. So it for this example, it will only reach convergence until 17th iteration or 20th iteration, if I may recall. But for this example, I only considered 7th iteration. So this is the essence of bisection method. This is the first stage of numerical analysis in calculus. And as we move forward, we'll discuss more complex methods such as Newton-Raphson's method and secant method. But always remember that that bisection method as your steadfast starting point in numerical root finding methods in calculus. So for the next session, we're going to discuss Newton-Raphson, and if you have questions, don't hesitate to ask me, and uh, don't hesitate to ask, and we love to ask your questions. And that's all, and thank you. See you next week.